All right, so here we're going to get into some visual models of work. So let's say that we have an object that is thrown straight upward. It reaches some maximum height and then falls back down to the ground. Now, we know through symmetry and kinematics that whatever the launch speed is, that's the speed that we also approach the ground with, and we know that our velocity at the top is 0. So now that we know what work is, our bar charts are going to look a little bit different. Okay? So how do I want to do this? Okay, so let's say we have 3 locations, A, B, and C. So A, B, and C, and then this is like the in-between, A to B and B to C. So let's say that our system is the Earth object system. So if that's the Earth object system, then that means I can consider UG and kinetic energy in my bar chart. Okay? And if I also think about the forces acting on the object, the only force acting on this object as it rises and falls is the force of gravity. So the work being done throughout this path should be 0. Okay? So at location A, I have all kinetic energy. At location B, that kinetic energy has converted completely to potential. And then at C again, I have all kinetic. Okay? And again, between A and B, there's no work being done, and between B and C, there's no work being done. So that's one way that we can analyze this system. Another way that we could analyze this system is if this system is the object-only system. Okay? And if that's the case, then FG is now external to the system. So gravity has the capability of possibly doing work. Okay? Now again, it's only going to do work if the force of gravity and the displacement are parallel, which in this case they are. So we are going to start, the object-only system does have kinetic energy at the beginning. Okay? But then between, let me move that out of the way, FG is external. Okay. But then between A and B, we have that force of gravity doing work. Okay? Between A and B, we have work done by the force of gravity. Okay? We are moving upwards, but have a force of gravity downwards, so that means that negative work is being done. Now, if I think about the energy I have at B, my kinetic energy is completely 0. So what that means is that gravity has done negative work on us, exactly equal to the amount of kinetic energy we had. Then on the way back down, gravity is in the same direction as the displacement, both downwards, and my kinetic energy at C has to be back equal to what it was at A. So that means between B and C, gravity has to do positive work equal to the amount of kinetic energy I gain back. So we could either consider this an Earth object system and kind of consider the transformation between kinetic and potential, or we can consider this as an object-only system where gravity is doing work on the object. So we go from all kinetic, and then as we rise from A to B, gravity does work, so we have 0 kinetic at B. Then gravity does positive work as we go from B to C, and we get all of our kinetic energy back at C. Okay. So the way I would calculate that work done by the force of gravity, remember I would set that equal to the change in kinetic energy here, because that's the energy that I'm changing. And so I would say, okay, the force of gravity times the height is equal to the change in kinetic energy. What's force of gravity? mgh. And we see the equation that we are most often used to. So that's kind of just another way that we know that it is correct. Okay. Now, from A to B, if we're thinking about our object-only system, the mechanical energy would decrease because our kinetic energy decreases to 0. And then from B to C, our mechanical energy would increase. Now our mechanical energy is changing because work is being done. Okay. In the object Earth system, between A and B and C, the mechanical energy is constant because there's no external forces. So let's take a look at another example. Okay, let's say that I have an object moving at a speed, boop, approaching a hill that has friction on it. So we're moving at a, there we go. Okay, so we are approaching a hill. So this travels up an incline, and let's say we wanted to analyze the object Earth system between when we are at this location and when we reach our maximum height. Okay, so if we're dealing with the object Earth system, that means that we can have kinetic energy, and force of gravity is internal, so I'm going to store that in potential energy. So instead of gravity doing work, it gets stored as potential. But I didn't include the surface in my system, so that means the force of friction is external. And yes, technically the normal force is also external, but remember the normal force does no work, but the force of friction is going to do work, and specifically it's going to do negative work. Okay. So here is my bar chart for A, bar chart for B, and then any work done A to B. Okay. So initially at position A, I start with kinetic energy. And then at position B, I have no kinetic energy because I'm at rest. But at position B, I am at a height, so I do have potential. Now what we're used to doing is we're used to just drawing a same-sized bar. But what we have to remember is that we have friction acting, and friction is going to do some negative work. So friction is going to do some negative work, right, which I'm going to draw as that bar, which is below 0. And however much work friction does, like let's say, I don't know, this is 8 bars and this is 3 bars, so that means I am left, this isn't really to scale, with 5 bars of UG, because friction stole 3 units of energy, so I only have 5 units left, right? So really what I'm saying is that the kinetic energy plus the work done by friction has to equal my gravitational potential at B. Now, if I analyze this as the object-only system, right, then that would mean the force of friction and the force of gravity both do work. Friction is negative work because friction is pointing down the incline as I travel up it. And gravity, specifically Fg parallel, points down the incline while I'm going up it, so gravity is also going to do negative work. So the difference here is that at location A, I still have those 8 bars, so to speak, of kinetic energy. But now at location B, when I'm at rest, I have 0 of Ke. So the amount of work being done by friction and gravity has to completely take all of my energy. So we're still going to have that -3 from friction, and then instead of storing some of that energy and potential, it now becomes energy leaving the system or work being done by the force of gravity, and I'm left with 0 at the end. So one other thing I wanted to talk about real quick in this video is a graph analysis that we do with work. So a lot of times when we're dealing with non-constant forces, meaning like a force is applied and it increases as time goes on, we pull harder and harder, maybe it looks something like this. Okay? When we have a non-constant force, the equation for work doesn't work. We can't use it because this force here is only for a constant force. So if we have a non-constant force, then we're going to graph force versus displacement. Okay? So the area of this graph would be change in y times change in x, or in this case, F times d, which is the work, or the change in energy. So if we're graphing force versus displacement, that area is work. So if we have positive area, that's going to mean positive work, which is going to mean an increase in energy. If we have negative area, that's going to mean negative work, which is going to mean a decrease in energy. Okay. Now, one thing I want to say is make sure that you watch out for the label here. Sometimes they will write this as the applied force. Sometimes this will be like net force. Sometimes they'll do it as F cosine theta. But the reason why I say that is because sometimes the area here won't exactly equal the change in energy we expect, right? And if that's the case, then that means that this y-axis is a single force and not a net force. So if you find the area here and it's not equal to the change in energy you expect, that means that there's some other force that you're not considering that's doing work on your system. Okay. So we can use this graph to help us find the V final of a specific object. A lot of times, let's see, this is 10 meters, 30 meters, and I don't know, let's say this is 20 newtons. So let's say we have an object that's initially moving at 5 meters a second. That object has a mass of 2 kilograms, and I want to know what the final velocity is. Okay. Now, I can't necessarily use an acceleration because it's not a constant force, so it's a non-constant acceleration, which is why we're using energy. So what I want to keep in mind here is that the total area being done is going to equal my change in energy, specifically my change in kinetic energy. So for area, I have this triangle plus this rectangle over that 30 meters. So I have 1/2 10 meters times 20 newtons plus 20 meters times 20 newtons. And the change in kinetic energy is going to be the final kinetic energy minus the initial. So 1/2 2 kilograms mv finals is what I'm looking for. And then minus 1/2 2 kilograms 5 meters a second squared. All right. So let's see, 5 times 20 is 100 plus 400 is V final squared minus 25. So this is 500 V final squared. So I add 25 to both sides. And then I would square root both sides. And in my calculator, I would figure out what the V final is. Okay. Last thing I want to talk about is the work done by a spring. So what do we do if our spring is not in our system? Now what you might think we do is just do the spring force times the displacement, but what we have to keep in mind is that that is a non-constant force. So what we would really need to do is an area of spring force versus X graph to find the work done by a spring. Okay, so I would have spring force, X, and I'll get this nice lovely line, and then the area would equal 1/2 the maximum spring force at the maximum stretch. Right, now I'm going to show you something cool. We know that that's how we need to find the work done by the spring, because work done by a spring external to the system should be equal to the change in potential energy of the springs inside the system. So 1/2 spring force is really kx times another x. Oh look, that area is really 1/2 kx squared, or the spring energy stored in a system. So all that to say, the work done by the spring is actually 1/2 spring force times x, or 1/2 kx squared. Okay, and that's because that spring force is not constant as it is stretched.